Okay, I want to do one more thing with the derivative form of the momentum principle before we start talking about our second fundamental principle, which will be the energy principle. And what I want to show you is just another thing you can do with this dp dt equals F net. Now, last week you worked with masses and springs in lab, and you saw them oscillating, and you discovered that the period of the oscillations depended both on the mass you had attached to the spring and the stiffness of the spring. If you hung two springs in parallel, you got a different period. If you strung two springs together in series, you got a different period, right? So one thing we'd like to have is an algebraic and analytical expression for the oscillations of a mass on a spring. And it turns out we can actually derive one using the momentum principle. Now we're going to consider a slightly simpler situation, although the results come out the same. We're going to consider an oscillator that's oscillating in the x direction without friction. And the reason we're going to do that is then we actually aren't going to have to worry about gravitational force in addition to the spring force. We're just going to worry about the spring force here. So, and we're going to be a little bit clever about how we do this to make the math easier. So we're going to have a mass on a spring oscillating horizontally on an extremely low friction surface. Maybe it's an air table or something. And so we're going to work with x components. And we're going to choose our coordinate system a little bit cleverly, just to make our lives a little simpler. We're going to choose x equals 0 to be at the end of the relaxed spring. So if the spring is just sitting there relaxed, we're going to put the origin right here. Okay? And then, so the length of the spring when it's stretched or compressed, the length of the spring is going to be equal to L0 plus x. So if x is greater than 0, the length is longer than L0. If the spring is compressed, then x is going to be negative and L is going to be less than L0. And therefore, the stretch, which is equal to L minus L0, is going to be L0 plus x minus L0, which is just equal to x. So x is going to be the stretch of the spring. And what we're looking for is some expression that tells us where the mass attached to the spring is going to be as a function of time. So we're looking for some solution that says x of t is some function of t. Okay, so that's our goal, to get there from the momentum principle. Now, the spring force as a vector here is going to be minus k sub s times L hat. And L hat is, of course, the vector that starts at the fixed end of the spring and goes to the end that's moving that you care about. So L hat in this case is just 1, 0, 0. And so the x component of the spring force is just minus k sub s times x, because x is the stretch, times 1. Okay, so we've just chosen our coordinate system a little bit cleverly to simplify math here. And the only unbalanced force acting on the block is, of course, going to be the spring force, because we have a gravitational force down, but we have the force by the table up, and those two forces are equal and opposite, which we know because the momentum isn't changing in the y direction. So the only force we have to worry about is the spring force, which can be in either direction, okay? So we can just worry about x directions, and so we can say dpx dt is f net x, and that's just going to be equal to the spring force. Okay? Now, this thing is moving slowly compared to the speed of light. So therefore, dpx dt is equal to the time derivative of mvx, or m dvx dt. But vx is actually the time derivative of x. So we can rewrite this as because so what we've ended up with here is, on the left-hand side of our equation, we have an m times the second derivative with respect to time of x. And on the right-hand side of our equation, we've got a minus k sub s times x. And we can rearrange just a little bit. By just moving the m to the other side of the equation. So this equation turns into that equation. Okay, we still haven't solved anything. We've just rewritten the equation. And this is what's called a second-order differential equation, because it involves a derivative and involves a second derivative. Okay, so how do you solve a differential equation like this? Well, there are a number of methods, but one legitimate method, which you'll learn if you take a course of differential equations, is actually to guess a solution, plug it in, and see if it works. And so what we need is some function whose second derivative is itself, except for a minus sign, kind of. So let's guess a solution that x is going to be a cosine function, so cosine of time, because the first derivative of cosine is sine, the second derivative gets you as minus sine, the second derivative gets you back to cosine, but with that minus sign there. Now, this is fine if this block moves 1 meter in either direction, but if it doesn't move 1 meter in either direction, we need some scale factor to say how far it actually moves, and that's usually called an A. It's called the amplitude of the motion, and amplitude is just how far it gets away from the equilibrium point. not quite right because the period might not be 2 pi seconds. So we need to put in something here that, so we really want something that's 2 pi over the period times t. We use a capital T for the period. This is called the amplitude. And conventionally, this thing, 2 pi over t, is symbolized by the Greek lowercase omega, which is an angular frequency. It has units of radians per second. So basically, we're guessing x is some amplitude times cosine of 2 pi over the period times t. With it so far? So how do we check? Well, we just plug it back into our equation and check. So our equation now looks like d squared dt squared of a cosine of omega t is equal to minus the spring stiffness over the mass attached to it times a cosine of omega t. And so we differentiate. So our first derivative here of a cosine omega t with respect to time gives us what? So we've got negative sine, and the a is still there, and we also have omega coming out, right? So that was what we got when we differentiated once. Now we do it again, and we get a minus a omega squared cosine omega t equals minus k sub s over m a cosine omega t. And this works if what? So we get rid of everything that's the same on both sides of the equation. So we've got the minus sign is the same, the a is the same, the cosine of omega t is the same. So we're left with an omega squared is equal to the spring stiffness over the mass, which would mean omega is equal to stiffness divided by the mass. And then this would be a solution. And that would suggest, since omega is 2 pi over our period, then the period is going to be 2 pi over omega. So that's going to be 2 pi times the square root of, and this is the thing that's most normally talked about when we talk about masses and springs. A mass on a spring, this ideal kind of spring that really has a force that's linear with the stretch, is called a harmonic oscillator. And so let's see if this makes sense. Do you remember what happened? So we have that the period depends on the mass and the spring stiffness. So if you had a spring with a mass on it, and you measured the period, and then you put a heavier mass on it, measured the period get longer or shorter? Did it go much faster?
Longer.
It was longer, wasn't it? And this makes sense because it says if the mass is greater, this period is going to get greater. What if you made the spring stiffer by putting two springs in parallel? Did anybody actually get to do that? Yeah. What happened to the period with the same mass? The period got shorter, right? So that makes some sense. So it looks like we've derived an equation that might, using this derivative form of the momentum principle, that actually gives us an analytical description of the behavior of a mass attached to a spring oscillating. And furthermore, it tells us what's going to happen if we increase the mass or spring. And if we plot x versus t, it's of course going to look like that, and that makes sense. You started the oscillation by stretching the spring, so that makes some sense. And this distance here, that's the period, and the maximum displacement from, it's called the amplitude. Okay, so let's, yeah. So let's see if we can answer some questions. Suppose you have a spring mass oscillator whose period is 1 second, and what happens if you double the mass? What's the new period? I hope the phones I see are being used as calculators. Well, we have period 1 is 2 pi times so what's the answer? Fingers, 2, 3, 4, 5, 6, 10, 20. Yeah, it's going to be 2 pi times the square root of 2m of s, and so we have this factor of square root of 2. So it's 1.4 seconds, right? What happens if we double the spring stiffness by using 2 springs? Now we have the original mass, but twice the spring stiffness. Fingers, 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 6, 10, 5. Yep, that's right. So T, we'll call that T3, is 2 pi times the square root of m over 2 k sub s. So the factor is 1 over the square root of 2. So it's indeed 0.7 seconds. So you made the spring stiffer, it got faster, right? So what happens if this original thing was oscillating with an amplitude of 5 centimeters, but now you started it with a stretch of 10 centimeters, so its amplitude's 10 centimeters. What happens to the period?
Because it's not depending on the.
Okay, so what's the period? Boy, you guys are hard to fool. Yeah, you're right. There's absolutely, A just isn't, the amplitude doesn't appear in this expression, does it? It's just not there, and sometimes what's not in an equation is just important as what is in an equation. So in fact, the interesting thing about this harmonic oscillator is that the period's going to be exactly the same even if we increase the amplitude by stretching it more. But it has to go farther. So how does that work? If it has to go farther in the same time, got to go faster, doesn't it? And that makes sense because the force is a lot bigger if you stretched it twice as far. So, okay, questions about that? Yes.
Could you go over what a harmonic oscillator is again, what it means?
Harmonic oscillator is just a mass on a spring, so it's just it's just this system. A spring, a mass attached to a spring that works like an ideal spring, so the force really is minus k sub s times the stretch times L hat, okay? And sooner or later, a real spring isn't going to do that. You stretch it far enough, all the coils straighten out, or you compress it too far and the coils all hit each other like the one you used in lab. So harmonic oscillator just means a system like this, where the spring force is always that, regardless of how tiny or how big the stretch is. Other questions? Okay, and now for something completely different. Do you know the Monty Python skit that starts that one? Never mind. So up until now, we've done everything with the momentum principle. And it's not going to go away. We're going to keep using it. But we did see at least one thing that we couldn't actually solve exactly with just the momentum principle alone, and that was using conservation of momentum in a collision. We had a head-on collision of two carts. Using conservation of momentum, if we knew the final momentum of one cart, we could tell you the momentum of the other, or two stars or whatever. But we couldn't actually predict it. We just didn't have enough equations to predict it if we didn't know the momentum of one. And what we need is another principle, and that principle, you probably won't be terribly surprised to know, is the energy principle. So what's energy? It's pretty much what you think it is. Okay, no free lunch. Got to expend energy to make things happen. So in formal terms, the energy principle we can write we can write it in several ways. We can write it as the change in energy of our system plus the change in energy of our surroundings equals 0. We can write it as the change in energy of the system is the sum of all the inputs from the surroundings. Or we could write E in some final state is E of the system in some initial state plus inputs. And so our task today is twofold. One is to be able to calculate the energy of a system, a simple system. We're going to start with a single particle. And second, to start being able to calculate some of the ways energy can be input to a system from the surroundings. So that's what we're going to work on. So as before, the simplest possible system we could consider is one particle. And everything else is the surroundings. A particle can either sit still or it can move. It can't get hot, it can't rotate, it can't vibrate, it can't translate. It's just this point particle. So it's really very simple. So what is the energy of a single particle? Or some system that we're modeling as a single particle. Well, the energy of a single particle is in fact gamma mc squared, where gamma is our old friend gamma. Gamma is equal to 1 over the square root of 1 minus v squared over c squared. And here I'm using the undecorated v to mean the magnitude of the velocity, so it's the speed. And remember, we know that the full definition of momentum is gamma mv, and that matters if things are going fast. Now, there's one difference that should jump out immediately. Momentum's a vector, but energy is not a vector. Energy is a scalar. That makes it easier to work with. Energy doesn't have a direction, so going in the x direction, going in the y direction doesn't matter. So what if this is the energy of a particle, and let's put it up here. What would be the energy of a particle that is at rest? So where does speed come into this equation? Speed comes into the equation in gamma, doesn't it? So let's see what happens to gamma if the particle's at rest. So v is 0. So now we have 1 minus 0. The square root of 1 is 1. We have 1 over 1, so gamma is exactly 1. So at rest, the energy of a particle that's at rest is 1 times mc squared, or mc squared. So the E equals mc squared, the rest energy of a particle. Well, if this is the total energy of a particle, and this is the rest energy of a particle, then what's the energy of a particle that's associated with its motion, that changes as its speed gets bigger? Well, that's so this is total energy. This is the rest energy. So that's just going to be gamma mc squared, which is the total energy, minus mc squared. And we call this kinetic energy. And that's just kind of a fancy word that comes from the Greek word for motion. So it really means energy associated with motion. The energy that... So let's put this up here. So let's just do some calculations and see what we've got here. All right, so let's consider an electron moving with a speed that's to the speed of light. So how would we calculate its total energy, and its rest energy? So take a minute and just write down what you would calculate even if you don't actually have a calculator. If you do, then by all means. Yes, the speed of light is 3 times 10 per second. Okay, so how do we calculate its rest energy? Okay, so rest energy is mc squared, so that's 9 times 10 to the minus 31 kilograms times 3 times 10 to the 8th meters per second squared. Does anybody actually have an answer? Or should we?
8.1 negative 14.
Okay. So 8.1 times 10 to the minus 14. What are the units of energy? You know? Joules. That's correct. So J, a joule is a unit of energy. Okay, what's its total energy? How do we calculate that? Gamma mc squared. So we have 1 over the square root of 1 minus. Now notice that we know the ratio of V to C. So V over C is 0.9, right? So we can just take 0.9 squared times mc squared, which we already know. Is this number going to be bigger or smaller than mc squared? Smaller, really? Bigger because it takes into effect motion. Has anyone actually calculated? Let's just do it. Okay. Okay, so we have mass is 9 times 10 to the minus 31 kilograms. C is 3 times 10 to the 8th meters per second. Gamma is 1 over the square root of 1, we'll say here, V over C is 0.9. 1 minus V over C squared. So let's print gamma. And total energy is gamma times m times c squared, print E total. Okay, does that look right? Okay. So we run it and we get, so gamma's big. And the total is, here let's write it as 18.6 times 10 to the minus 14 joules. So it's a lot. Yeah, it's a lot bigger. So how would we get the kinetic energy? It's going to be gamma mc squared minus mc squared, right? So let's calculate that. So that's 10.5 times 10 to the minus 14 joules. It's a difference between that and that. Okay, so we can calculate energy. Questions about that? Yes?
What's the energy of a photon since it's traveling at the speed of light?
Ah, okay, so what's the energy of a photon since it's traveling at the speed of light? We can't use this equation to calculate it. We have to, photons actually, it turns out, have energy and momentum, but they have zero rest mass, meaning they can't be at rest. So they carry both energy and momentum. So we have to calculate the energy of a photon a different way, which we will actually talk about. Okay, so questions? All right, fine. So let's take a different situation. So let's take a more ordinary situation. We have a ball. Its mass is 2 kilograms. Its velocity is 3 meters per second. What's its rest energy, its total particle energy, and its kinetic energy? So its speed is going to be the square root of 3 squared plus minus 3 quantity squared plus 4 squared is going to be 5 meters per second. So basically, its rest energy is mc squared, so that's 2 kilograms times 3 times 10 to the 8th meters per second squared. Its total energy is gamma mc squared. But what's gamma here? I mean, it's traveling 5 meters per second. Gamma's basically 1, isn't it? So that's basically going to be 1 times 2 kilograms times 3 times 10 to the 8th meters per second squared. And so its kinetic energy looks like that's going to be this minus that. Looks like it's going to be 0. That can't be right. The problem is here that calculating gamma to enough significant figures is actually almost impossible. If you try to do it on the computer, it will give you a number, but that number is actually going to be garbage down in the lower digits, because floating point numbers, real numbers like this, actually only have are only really represented accurately to about 15 digits. And to get gamma accurate, in most computer representations or calculators, to get gamma accurately, you'd need 18 or 20 or more. And so that's a problem. So we don't want the kinetic energy to come out to 0. So we need to worry about that. And to solve this problem, we need to do a little bit of math. Because what comes to our rescue is the binomial expansion. So remember that from some math course or other, if you have an expression like 1 plus some incredibly small number, epsilon, to the nth, you can write it as a sum of a series, which is 1 plus n times epsilon plus, what is it, n times n minus 1 over 2 epsilon squared plus a whole bunch of other terms. Well, we can kind of write gamma. I mean, since the ratio of v over c is actually very tiny here, then in gamma, that 1 minus v over c kind of looks like a 1 plus an epsilon. So if we write gamma this way, gamma is equal to 1 plus minus v squared over c squared to the negative half. Then we can say, well, epsilon here is minus v squared over c squared, and n is just minus a half. And so we can expand this out as 1 plus n times epsilon. So we have minus a half times a minus v squared over c squared plus a whole bunch of other terms that we're going to ignore. So we're just going to take the first 2 terms of this. And so what we're going to get here is gamma mc squared is going to be equal to approximately a half v squared over c squared times mc squared. So that's going to be mc squared plus a half v squared over c squared times squared. So that's going to be equal to mc squared plus, the c squareds cancel, a half mv squared. And so the kinetic energy, which is just gamma mc squared minus mc squared, is this quantity minus mc squared. And it just comes out to approximately a half mv squared. As long as the speed is much less than the speed of light. So as long as this quantity is really small. So at ordinary speeds, we can calculate the kinetic energy, the additional energy to the rest energy. So here's our rest energy. And here's our kinetic energy. So let's go back to the ball. The kinetic energy, now how do we calculate the kinetic energy? So it's a half times 2 kilograms times 5 meters per second squared, which is equal to 25 joules. Its rest energy is 2 kilograms times 3 times 10 to the 8th meters per second squared. So square this is 9 times 10 to the 16th. So we have 18 times 10 to the 16th, so 1.8 times 10 to the 17. For the fast-moving electron, we saw that its kinetic energy was bigger than its rest energy, but for this slow-moving ball, its rest energy is huge compared to its kinetic energy. Now, rest energy is important because that's the energy that can be released in things like nuclear reactions. Since most of the mass is associated with the nucleus, that's where the energy in a nuclear reaction comes from, a change in rest energy of the object. Some of that mass gets converted to kinetic energy or to energetic photons coming out or things like that. And we'll talk more about nuclear reactions as we go on. So fortunately, there's a super ordinary way to do this. Now, it's worth noting, so let's put this up here. Kinetic energy is a half mv squared. I guess I should try to write a better 2. If speed is less than the speed of light. Okay, so we can calculate rest energy. And notice also, this is useful to note, that since momentum at these speeds is equal to m times v, a half mv squared is actually equal to the magnitude of the momentum squared over 2m. Which is kind of a useful thing to keep in mind if you okay, so we can calculate energy. But how do we change it? So what is this inputs from the surroundings thing? Well, it turns out there's a number of ways to do it, but one way to do it is simply by doing what we call mechanical work on a system. So what is work? Well, up until now, we've been talking about force. So change in momentum, it required a net force acting for some time. It turns out that a change in energy can be caused by a net force acting through some displacement. So, and this is defined as work. Now that is indeed the vector dot product that we saw when we were talking about parallel and perpendicular components of force and momentum. And so what this really comes down to is work is a force applied in the x direction times through a displacement in the x direction plus a force in the y direction through a displacement in the y direction plus fz delta z. So what does that mean? Well, let's think, just take something very concrete. So here's a cup of tea. If I lift it a distance delta y, it does require some energy to do that. Okay, so I did work on this cup to lift it that distance. If I lift it twice as far, I've done twice as much work. So that's basically all that equation says. But there are some nuances that we need to work out. So let's look at some examples and calculate work. Okay. Okay. So you're on a space station and you push a box that's initially at location 0010 meters to location 0014 meters, applying a force of 5 newtons how much work did you do on the box? Okay, answers? Okay, mostly people say 1, and that's correct. So we have, just our definition says work is the force in the x direction times the x displacement, that was 0, plus the force in the y direction times the y displacement, that was also 0, plus the x component, the z component of your force, which is 5 newtons, times the displacement in the z direction, which is 14 minus 10 meters. And so that looks like 5 times 4. So that looks like 20 newton meters. So a newton times a meter must be a joule. So according to the energy principle, if we're the only thing interacting with this box, how much did the energy of the box change? $20 joules. 20 joules. So, and it increased by 20 joules, right? That's a positive 20 joules. Can we tell how fast the box is moving now? Is that kinetic? Is that a change in kinetic energy or a change in rest energy of the box? Can we change the rest energy of a box? Can we change its mass? No. So change of kinetic energy, right? So it's moving faster. Can we tell how fast it's moving now? What would we need to know in order to calculate how fast the speed of the box now? Okay, so if we want to know the speed of the box, the final speed of the box, well, we know that we know the change in its kinetic energy, and kinetic energy does involve speed, doesn't it? But we only know a change. So what things would we need to know in addition to the change in kinetic energy before we could calculate its final speed? We need to know the mass of the box. So we need to know the mass of the box. Is there anything else we need to know? The initial kinetic energy, so basically how fast it was going initially, right? We do need to know the initial kinetic energy. Okay, so this is the change in kinetic energy, and that's a change in half mv squared. So let's make up some numbers and see what we get. So let's say the mass of the box is 2 kilograms, and let's say its initial speed was 2 meters per second. Now can we calculate how fast it's moving after we did this work on it? Yeah, we can, can't we? Now what we're really doing here is applying the energy principle, and let's be a little formal about it, because we're actually going to solve every energy principle problem exactly the same way. So that makes them kind of easy, because you can always do the same thing. So we're going to say the final energy of the system is the initial energy of the system plus inputs, work, or whatever else. And so what's our system? Well, our system is the box. And so we have, what's the final energy? Well, it's the rest energy plus the final kinetic energy. What was its initial energy? Well, it was its rest energy plus its initial kinetic energy plus the work we just did. Now, you may think it's a little silly to write out the rest energy in a case where we know the rest energy isn't changing, but it actually helps us just make sure that we've counted everything, and we're going to do problems where the rest energy does change. So now we've got quantities we've got this equation, we've fleshed out the energy principle, and we know that the unknown we're looking for, this is sort of a Where's Waldo game. Well, the unknown is actually inside this final kinetic energy. So those things are the same and they cancel out. The final kinetic energy is, now we can half times 2 kilograms times 2 meters per second squared plus the amount of work we did, which was 20 joules. So this gives us, the 2's cancel. We have 4 joules is its initial kinetic energy plus 20 joules is 24 joules, and this is a half times 2 kilograms times V final squared. So V final is going to be the square root of 24, which is going to be something like 4.9 meters per second. So the energy principle is an incredibly straightforward problem-solving tool if we use it systematically. So questions so far? Okay, so there's a twist to this work thing. So let's think about a couple of situations involving work. So we have a figure skater who's sliding in the negative x direction along the ice toward her partner, and when she gets close, he pushes on her in the plus x direction to slow her down. What's the sign of the work that her partner does? So is it positive, negative, or 0? Okay, let's vote here. Okay, don't see very many votes, but I see votes for 1, 2, and 3. So let's talk about it. Okay, so let's be super concrete here. So f of x, so he's pushing in the plus x direction. So let's say this is a plus 3, the x component of f is plus 3 newtons. She's moving in the minus x direction. So let's say, which is x final minus x initial, is she ends up at 2 meters, but she started at 4 meters, so that's a minus 2 meters because she's moving in the negative x direction. So therefore, Fx delta x is 3 newtons times a minus 2 meters, which is a negative 6 joules, right? So it looks like work can be negative. So what does that mean? What does negative work do?
Lowers kinetic energy.
Exactly. It just lowers the final kinetic energy is the initial energy plus work if work is negative. And the final kinetic energy is just going to be less than the initial kinetic energy. So negative work is a thing. It's a totally legitimate thing. And we have to be super, super, super careful about signs. Connor, do you have a question? Yeah.
Yeah, I'm having a hard time like picturing this. Like, so the guy who's stopping the girl, or the guy who's stopping the figure skater, he would be doing positive work to himself, though, right?
No, he's the work. So you have to choose. Work is very careful. We have to be really careful, and you're raising a good point. We've picked. So what do we pick as the system here? The figure skater, right? So the work done on the figure skater is calculated. So we have our diagram up here. We have her displacement is to the left, but the force he's exerting is to the right. So the force is opposite the displacement. So the work he does is negative. Now he has to expend, if you take him as the system, what's changed about him? He's burning chemical energy to do this, right? So his own internal energy, which we aren't prepared to talk about yet because we're modeling everything as a particle which doesn't have internal energy, but we'll get there, has to decrease, right? So he's expending energy. So, but if we take the figure skater as the system, she's moving this way, you're pushing that way, but you're exerting a force through that displacement, so you're actually doing negative work. So this is a lot about signs in book. Force opposite the displacement. Work ends up being negative. Okay, so fan cart, like the ones you used in lab. The fan's on. The force on the cart by the air is in the minus x direction. Is the work done by, so here's our force diagram and our displacement. Is the work done by the air positive, negative, or 0? Okay, I see a lot of you answering. To the person next to you for just a minute. Okay, so what do we got? Okay, so you're saying positive, number one, that's correct. So basically what we've got is that the x component of the force is now negative, right? It is still, delta x is still a negative number. So we have a negative 3 newtons times, so the work done is indeed positive. So what happens to your fan cart? Does it speed up or slow down? Speeds up, because positive work was done on it by the air. Okay, a tennis ball is moving in the negative y direction, and you actually hit it downward as it's moving. Okay, what's the answer? Work positive, negative? Yep, positive work, you're exactly right. So we have, just to make up some numbers, Fy is minus 3 newtons, delta y is negative, because it's, so minus 2 meters, so work is minus 3 newtons, minus 2 meters, plus 6 joules. So what happened to the kinetic energy of the tennis ball? Went up. What happened to its speed? Went up. Okay. So this doesn't, the sign of work is not the sign of the force component, and it's not the sign of delta x. It's the combination, and basically if the displacement is in the same direction as the force, work ends up being positive. But if the displacement is opposite to the force, it ends up being negative. So one last example, here's a skydiver falling toward Earth. His parachute open. During his fall, does the force by the air do positive, negative, or zero work on the skydiver? Okay, all right, I'm seeing all twos, excellent. So yes, the work is negative because the force is up, but delta y is less than 0, Fy is greater than 0. Okay, so you've got, yes. Is there an example of when work is 0? That's a great question. Can you think of one? Okay, when there's no force, that's a trivial one. But let's consider the following situation. Here's a block sliding to the right. So it's sliding in the plus x direction. With a downward force. So your force is in the y direction. So let's calculate the work. So work is Fx delta x plus Fy delta y plus Fz delta z. So delta x is positive, but Fx is 0. So that term comes out to 0. Fy is negative, but it doesn't move in the y direction, so delta y is 0. So that term comes out to 0, and these are both 0. So it looks like a force perpendicular to the motion does 0 work. Now those of you who did this week's lab already, so Monday lab, wake up. You ended up at one point with a spacecraft in a circular orbit around the Earth, right? Okay, so here's, at this point, say, here's the velocity of the spacecraft. What's the direction of the force the Earth is exerting on it? Down. So the force is actually exerted by the Earth is perpendicular to the instantaneous velocity. So how much work does that force do? So how much does the kinetic energy of the spacecraft change? It goes around at constant speed. So this is an example. So that was a great question, Hunter. It's an example of a situation where if a force is truly perpendicular to the displacement, as this is instantaneously at all times, zero work is done and the kinetic energy of the system doesn't change. Okay, we'll work on this in recitation.